Well, hello everybody, welcome. Today I sort of want to do a project with you, a little bit of a different format, and I think you'll actually have fun. But rather than just have you watch me do the project, I'd like you to join with me and do it yourself as well. Because if you can do the project yourself, and if you can make the discovery that I'm going to show you with your own mind, it'll actually be much better for you than if you just watch me do it. So take a few moments here and get yourself some materials together. What you would need is the following. Let's see here. You would need 2 sheets of graph paper, 3 colored pencils or markers, some scissors, some tape, and a calculator. So go ahead and press pause on the video and take a few moments and pull those things together, because I don't want to rob you of the joy of discovering this for yourself. So I'm going to leave it to you to do it if you can do it with me. So press pause. I will be right back. All right, moving my stuff out of the way, but all within easy reach. Okay, so start with your graph paper here. I've got a piece of, it's probably 1/4 inch grid, but you can be whatever you like. Just make sure it's not too big or too small, because some things need to fit here. This is probably a good size for what we're going to do. And over in the lower left-hand corner, I'm going to make a mark somewhere over in here. I got to give myself a little bit of a margin. I'll make a mark right here. Okay, now I'm going to count 5 units over and make another mark. 1, 2, 3, 4, 5, and make another mark. So the distance from the left point to the right point should be 5 grids. All right, now I'm going to count over 12. So 1, 2, 3. Oh wait, there's a song for that. Do you know the song? 1, 2, 3, 4, 5, 6, 7. Whoops, hang on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Let's try that one more time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Good. All right, so now go up 12 units from this marker. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And come over 12, and so basically what we're going to be doing is we're going to be making a 12 by 12 square here. Let's double check and count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We're in. All right, so carefully, especially on the corners. The corners need to be precise. Corners, I'm going to make myself a little square right here. By 12. You do the same thing on your sheet of graph paper. So this is going to be 12 here, and this is going to be 12 here. And take a moment and color it in. Pick one of the colors that you've got for your markers or whatnot, and color it in. I'm going to press pause and color mine in. You press pause, and you do the same. Okay, I've colored mine in. Color it in lightly, because I still want to be able to see the grid marks underneath here. Now, if it's a 12 by 12 square, how many individual little grid squares do I have inside here? You should see very clearly that that's 12 squared, which 12 to the second exponent, which is why that exponent is called square, because it gives you the area of a square. That would be 144. Isn't that so gross? Yes, it is, because a gross is a dozen, and so that's exactly gross, which is 144. So anyway, there we go. It's 144. Now, go up to the upper left-hand corner right here and count to the left 5 units. 1, 2, 3, 4, 5. Actually, it should line up with the mark down here. The only reason for this mark right there was to give us room to go to the left 5 units. So make yourself a mark 5 units left, and then from the same corner 5 units up. 1, 2, 3, 4, 5 units up, and then make a 5 by 5 square here. Be very careful on the corners. The corners can't be sloppy. Corners have to be precise. And then press pause on the video and lightly color that in. And I will do the same here in just a moment. Okay, now mine's colored in. This is a 5 by 5 square. So what is the area here in this blue square? or the number of grid marks, you should see that that's 25. Okay, good? All right, set this piece of paper aside. Get yourself the second sheet of paper, and I want you to mark out a 13 by 13 square. So I'm going to pick just anywhere in the middle. It's just got to fit. Be mindful of holes. You don't want any holes in the area. So I'm going to come over here, and I'm going to make a 13 by 13 square and do the same thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So then you're going to mark this off. You're going to then color that in, write the number of the area of square units in the middle, and then use your scissors and cut that guy out, right? Okay, press pause. I'll be right back. All right, I'm checking in. How you doing? Here's my square. I'm coloring it in red, 13 by 13, which makes the number of grids in the middle, or the area, 169. Okay, now, again, this one needs to be cut out. So be very, very careful, but on the corners, cut it out exactly on the lines. Okay, go for it. Press pause, get that guy cut out. Okay, here we go. A 169 square. Go get your other sheet of paper. Now these two go together. There is a very wonderful and special way that these squares go together. And so what I want you to do is I want you to, here, let me zoom out just a little bit. What I want you to do is I want you to find the way that these squares go together. And so take this square and do what you think you need to do with it, and press pause in the video, put it where you think it might go, and then press play again, and we'll see if you get it right. If you put it here, which is what most people do, no, that's not right. Where else could it go? Oh, it can go right here. Yeah, that's how they go together. No. And go like this. No. How do they go? I'll tell you what. Everything has to line up precisely. There is an exact way to put these together. It's not this, because I got like this extra part over here and this extra little one spot over here. There's something that you can do with these three squares so that this corner and this corner would line up, or this one or the top one. Somehow the corners all line up on top together. And it's not something like, you know, this where one's on top of the other one. It's not overlaid. There's no overlap. Where do you need to put these things so that they exactly line up corner to corner? Getting closer. Getting closer. In fact, if I take the corner right here and put it on this open corner right here, and take that corner of the red one right there and put it on that open corner right there, they will line up exactly corner to corner to corner. And now I'm going to use my tape, and I'm going to exactly mark this down. If you're a little sloppy with either drawing it or cutting it out or whatnot, it won't work. But if you did it precisely, they should fit. And get this one over here. And there we go. That, my friends, is the Pythagorean Theorem. Woohoo! You say, what? Like, I thought the Pythagorean Theorem was based upon a triangle. No, squares. Actually, what it is this. the area of the big square right here is exactly equal to the sum of the areas of these two squares, but only if you join them right there with a at a right angle. So here's the Pythagorean theorem. The Pythagorean theorem says that the area of the big one is equal to the area of the first one plus the area of the second one when you add them together. And I bet you $1 that if you add together 144 and 25, you would get 169. Okay? That's the Pythagorean theorem. The Pythagorean theorem is based upon areas of squares. If you take two squares and you join them at a right angle with on their corners here, then the square that you would get by connecting the open corners, this open corner with that open corner, the area of that square is exactly equal to the sum of the other two areas. Nifty, huh? But most of you are used to the Pythagorean theorem being a triangle. And if you look carefully, you can actually see a triangle. The triangle is right here. The triangle is the hole in the middle of the area of the squares. Now, I want to point something else out to you now. By the way, let me just run the numbers here. This was, area here was 169. That had to equal 25 plus 144. 169, that was 13 squared. And that has to be equal to 5 squared plus 12 squared. And so now, as you can see, if I call this side right here C, and I call the short little side then A, and I call the longer side, but not the longest side, B, then I get C squared is equal to A squared plus B squared. Nice, there's your Pythagorean theorem. Now, it's not just a number puzzle. It controls real space. As I showed you right here, like the squares go together, physical squares. It's not just some kind of abstract numbers that when I add them up, I get something that's the same thing. Like it's got real physical space associated with it. Let me show you another example. So let me do, I've got a sheet of centimeter grid paper right here. And if I use my centimeter ruler here, kind of come in a little closer. If I use my centimeter ruler here to double check, if I just put it on the end here and go from 1 to 1, can you see that this is grid lines a centimeter? So let's do something a little bit different. Let's do, let's say, start right here, and let's do 1, 2, 3, 4. 4 this way, so that's 4. And then let me go up, 1, 2, 3. And let me make a triangle, a right triangle, out of these, right there. And then that's 4, that's 3. My question is, how long is that side right there? Well, if we use the Pythagorean theorem, which as you know, says that this side length, the unknown, is equal to this side length here, 3 squared plus 4 squared. That's going to be 9 plus 16. That's equal to 25, and then it has to be the square root of this. This should be 5 units long. Is it? Let me be very, very precise. Put that right up there. Swing it over. It should be lining up. Look at that. 5 units long. It'll be the same for everything. How about this one? How about a 5 by 6? 1, 2, 3, 4, 5 here. And then up. 1, 2, 3, 4, 5, 6. And then I'll connect these. How long is that? If you want to do the Pythagorean theorem on this triangle right here, this is 5, this is 6, you wind up with what? The square root of 61 should be about 7.8 according to my mathematics. Let me come up here now and let me do this with the ruler. 7.8. Look, here's 7.8 right there. Is it on? It sure looks on to me. Why does this happen? Why does mathematics control physical space? Or let me say it a different way. Why does the physical world obey mathematics? That's wonderful. What's going on? You guys should read some Galileo or some Pascal or even some of the ancient mathematician Ptolemy. We discuss why that is. But it's wonderful. And it's wonderful, I think, that human beings can discover and use this connection between mathematics and the physical world. All right, now it's time to get serious with some problem-solving stuff. That was fun. Let's now go over to some notes and some problem-solving. Okay, so the Pythagorean Theorem, as we've seen, is what you get when you join two squares at a right angle in their corners, and then the area of the one is equal to the sum of the areas of the other two. So if I come in here, here's my figure, that's got to be a right angle, all right? And then I get c squared, the area of the big square is equal to a squared plus b squared. All right. And the triangle that we're talking about usually when you see it, that's actually the hole that's in the middle, right? And it works exactly. It's got a geometrical proof to it. So let's do a little bit of review here now. A right-angled triangle is a triangle which has a right angle as one of its angles. The side opposite the right angle is called the hypotenuse and the longest side of the triangle. And the other two sides are called the legs of the triangle. So now the way I want you to think about it when you do a right triangle problem is I want you to first, your eye needs to find the right angle. And you see a right angle, we're told it's a right angle because of that little square in the corner, right? Your eye needs to find that. Then the side that's opposite it is the hypotenuse. It's never one of the other two sides. The other two sides are called legs. Now, only right triangles have a hypotenuse. So I would change this. The hypotenuse is the longest side of this. Not any triangle, only a right triangle, only this triangle. If it's not a right triangle, it doesn't have a hypotenuse. I've seen students try to use the Pythagorean theorem on all kinds of triangles. So they'll have a triangle that looks like this, a big obtuse triangle. And they'll try to say, oh, this is A, and this is B, and this is C, and so C squared is equal to A squared plus B squared. No, that's not a hypotenuse. What's the longest side of the triangle? Yeah, lots of triangles have longest sides, but only a right triangle has a hypotenuse, and it is the longest side of a right triangle. But the longest side is not the definition of a hypotenuse. It's the side opposite the right angle. All right, so enough of that. Now, let's talk about how to do these with problem solving. So if I've got a right triangle here, how do I know that? I see the mark right there. I'm told it's certainly a right triangle. I need to find the missing side, all right? So my eye goes to the right angle. My eye then goes, or my mind goes to find the opposite side, and I write the formula down. C squared is equal to A squared plus B squared. You might have done it A squared plus B squared is equal to C squared. I'd like you to switch it. I'd like you to start with the hypotenuse first, because the hypotenuse is the most important part of the right triangle. So your mind needs to find that first. All right. Now I set it up by replacing the values in the formula with the things that I've got in the triangle. So I've got x squared. That has to be equal to 4 squared plus 7 squared. Doesn't matter what order you put the a and the b in. And so then I get x squared is equal to, what's that, 16 plus 49. And I get then in the end x squared is equal to 65. And then I solve this by square rooting both sides, so I get x is equal to the square root of 65, not plus or minus, because the x here in this case means a distance, and the distance can't be negative. So algebraically you'd get plus or minus, but when we're talking distances here, which means it's controlling real space, you don't have a negative one. So the exact answer would be the square root of 65, or if you're going to do an approximation, x is approximately equal to, I get 8.0623. Nice. How about one like this? Well, again, find the right angle. Look, there it is. Find the hypotenuse. Look, there it is. Lots of students will set this up wrong. They'll set it up by saying x squared is equal to something, 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 because they want to solve for x. And they should. They should solve for x. But you can't just set it up for the variable to be equal to whatever you get when you add the other two things together. Find the hypotenuse. The hypotenuse is not x, it's 11. Okay, so c squared is equal to a squared plus b squared. Where's c? Where's the hypotenuse? It's that one. It's 11 squared is equal to 6 squared plus x squared. Some of you are a little irritated at me because I'm putting parentheses around all the parts, and you're like, what are you doing that for? Trust me, you'll need it. You don't necessarily need it here, but you will later. It's a very good habit to get into. And if you don't do it when you need it, you'll get it wrong. So what have I got now on this one? I've got 121 is equal to 36 plus x squared. I do the math. I get x is equal to, say, the square root of 85. Or x is approximately equal to 9.2195. 9.2195. Let me think about this. Can this side be 9.2195? Well, it has to be shorter than the hypotenuse, because the hypotenuse is the longest side in any right triangle. Is it shorter than that? Yes, so it's reasonable. If you'd have gotten a bigger answer than 11, like 14 or something like that, you would have made a mistake somewhere. Several people would not square root both sides, so they would say x is equal to 85, which is impossible. How can one of the legs be much, much longer than the hypotenuse? Can't be. All right, how about this one? Find the right angle. There it is. Find the hypotenuse. There it is. Set it up. Use parentheses. C squared is equal to a squared plus b squared. Replace the c with what it is. What is it? 2x with parentheses squared is equal to 9 squared plus x squared. So if I simplify, this becomes 4x squared. Do you see now why I needed the parentheses? It's the entire group. The base is 2x, not just x. 4x squared is equal to 81 plus x squared. Subtract x squared. I get 3x squared is equal to 81. X squared is equal to 27. X then is equal to the square root of 27, which is 3 root 3. Or approximately 5.1962. Is that agreeable? Well, that would make this about 5, and that would make this about 10. Yeah, that makes sense, because the hypotenuse then has to be larger than 9. Okay? See how this is working out? Use parentheses. They're your friends. Oh no, now this one. Okay, find the right angle. Whoop, there it is. Find the hypotenuse. Right there. All right, same thing. C squared is equal to a squared plus b squared. Every time you use the formula, write the formula down. Now substitute. 13 squared is equal to, oh, now we got a binomial. X minus 2 squared plus 5 squared. Now simplify. Okay, so that's going to be 169 is equal to x squared minus 4. Is that what you said? Nope, you can't square just the pieces. You got to FOIL it out. It's x squared minus 4x minus 4 plus 25. And now I set the left-hand side equal to 0. 0 is equal to x squared minus 4x minus 140. You can solve it by the quadratic formula. You can solve it actually by factoring. Or actually right here at this point, you could have left this as a square, passed that to the other side by subtraction, and then square rooted both sides. But in any case, in the end, you should get x is equal to 14. Okay? Now, what about that one? Well, if a right triangle means that the Pythagorean theorem is true, if the Pythagorean theorem is true, then the triangle is a right triangle. So let's work this process backward. Is this triangle a right triangle? You're going to look at the picture and go, oh no, It doesn't look that way to me. But again, mathematics is not about how it looks to me. Mathematics is about certainty, right? So I can't just go by how the picture looks according to how it's drawn. I have to go with what I know for certain. Well, what I know for certain is the side lengths. Well, let's see if the side lengths satisfy the Pythagorean theorem. Well, what would be the hypotenuse then? Well, it has to be the longest of the sides. So that right there, 17, has to be your hypotenuse. So let's double check it. Let me just see here. C squared has to be equal to a squared plus b squared if it's a right triangle. And so that means 17 squared, is it? I don't know, I'm asking. See the question mark on top? I don't know. Is it equal to the one short side, 15 squared, plus 8 squared? I don't know. Let me run the numbers. You get your calculator and have to run your own numbers. So I'm getting 289 is equal to maybe 225 plus 64. And if I do that mathematics, 289 it actually is 225 plus 64. This is 289 over here. So is it a right triangle? Yes, it is. How do you know that? It satisfies the Pythagorean theorem. You can't just go by how it looks. You gotta do what you know for certain. Okay, now this is going to be interesting. What is the length of the longest toothpick which can be placed inside a rectangular box that's 3 by 5 by 8? Don't tell me 8. You're going to say, why not? That's the longest side. Yeah, but that's not the longest length available. When we do a box, well, let me draw a box here. You draw a box by taking two rectangles and drawing them one offset from another one, like that. And then you connect the corners, here to here, here to here, here to here, and then here to here. And then maybe let me shade the outside so that you can tell maybe if you're looking to the inside of a box. Yeah, it's a pretty good box. When you do a box, the length is always the longest side on the base. The width is always the middle number, and then the height is always the smaller of those numbers. If it can be arranged in any way. Now they may tell you like the open top box is different, but anyway, this is the most stable arrangement of a box. It won't tip over this way. You put it with any other base side as its bottom, besides the two longest ones, and you can tip it over. Right, this has got the lowest potential energy, but anyway, that's a physics consideration. Let's just look at the base. This is going to be like an 8 down here, and this is going to be like a 5. So what's the longest distance in that base of 8 by 5? Don't tell me 8, because looky here. If I do the diagonal, which if it's a rectangular base, that's a right angle. If I do a diagonal, then that's actually longer than 8, wouldn't it be? Okay, so then again, c squared is equal to a squared plus b squared. C squared is equal to 8 squared plus 5 squared. And so then if you do the math, c is equal to, what did I get? Square root of 89 exactly, or c is approximately then 9.4340. And 9 is longer than 8. Okay, but now it's not asking about that. It's actually asking about a box, not just a table, like what's the longest stick you can put on an 8 by 5 table. Well, the longest stick you can fit on there without overhang is 9.4340. But this is now inside a rectangular box, so it's now 3 dimensions. So what we have going on is we're looking for this dimension right here up in that corner, all the way down, dot, 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 dot. Oops, I didn't draw it quite right. Let me erase that. This one all the way down, dot, 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 inside the box to that corner right there, corner to corner, which means we then get this, right triangle right here, the height, and then the diagonal of the length and the width. So we already found that diagonal. Let me redraw the triangle just a little bit here. So this is going to be 3. And then this base is the one that we actually just found there. This is the square root of 89. So then I'm going to say y. What about that one right there? That's the distance from corner to corner, here to here. So then I do it twice. So then I have to say then that y squared is equal to square root of 89 squared plus 3 squared. So then y, when I do the math in the end, is the square root of 98, or approximately 9.8995. It's pretty good. Let me show you what I'm talking about. Maybe if I can get the document camera to do this. This will be a little fun. I got a box. Zoom way out. I got a box here. Okay. What I want to know is what's the longest thing that I can stick inside the box. It will actually be from corner up here to the inside corner. It would be this distance right there. Okay? Spin it around maybe so that you can see it a little bit. It'll be that distance right there. And I've marked out inside the right triangle that I need. I need to find the diagonal of the bottom, and then I need to take it by the side. But if I hold my finger right here and I get this length, look how much longer that is than the length of the box, and certainly longer than the width of the box, and certainly longer than the height of the box. It's quite a bit higher. Alrighty? That's a great question. All right. It's a long lesson. Maybe you could do this in 2 parts. I don't know. But it's good. The Pythagorean Theorem is one of those things that's got some good history behind it. There's some fantastic stories about that. Like the guy that used the Pythagorean Theorem to show that the Pythagorean philosophy had a flaw in it. You should read up on how they accepted him. But in any case, why does the physical world obey mathematics? And how is it possible that humans can have access to both the physical world and also the world of abstract mathematics through our minds, and can see the connection there between those, and can use it and put it to a good purpose? I think it's fantastic. Anyway, I hope you learned something, and let us pursue goodness, truth, and beauty.